Substructural logic is a broad family of non-classical logics obtained by modifying or rejecting certain structural rules that govern how premises may be used in reasoning. These rules do not concern the meanings of particular logical connectives, but rather the general structure of inference, how assumptions can be introduced, reused, reordered, or discarded in proofs. Classical logic fully validates all standard structural rules. Substructural logics arise when one or more of these rules are restricted or dropped, thereby yielding logics that are sensitive to relevance, resource usage, order, or direction of inference. A useful way to understand substructural logic is to distinguish structural rules from non-structural, logical rules. Non-structural rules govern the behavior of specific, logical connectives. A familiar example is modus ponens, from A and if A, then B, infer B. This rule concerns implication specifically, not the general handling of premises. Structural rules, by contrast, govern how premises may be manipulated independently of their content. They apply to any formulas whatsoever and thus shape the overall logic. Substructural logics typically keep most non-structural rules, but alter the structural ones. Several structural rules play a central role in classical logic. Understanding them informally helps clarify what substructural logics change. Identity. Any statement may be inferred from itself. If you assume A, you may conclude A. Cut. If A is derivable from X and B is derivable from Y, A, then B is derivable from X, Y, where X and Y are sets of sentences. Weakening. You may add extra premises without affecting validity. If B follows from A, then B also follows from A, together with any statement C. Contraction. You may use the same premise more than once. Having A available twice gives you no more than having it once. Commutativity. The order of premises does not matter. A and B together are equivalent to B and A. Associativity. Grouping of premises does not matter. Whether we group A and B and then C, or A and then B and C, makes no difference. Residuation. This connects implication-like operations with conjunction-like operations, allowing movement between assumptions and conclusions in a controlled way. B is derivable from X. A, if and only if. A implies B is derivable from X, where X is a set of sentences. Substructural logics typically reject or restrict one or more of these principles. There are several motivations for developing substructural logics. One is philosophical. Some inferences validated by classical logic seem to rely on irrelevant or duplicated premises. This motivates logics, such as relevance logic, that restrict weakening or contraction. Another motivation is resource sensitivity. In many contexts, such as computation, linguistics, or economics, premises represent resources that cannot be freely copied or discarded. Linear logic, for example, treats assumptions as consumable resources. A third motivation comes from language and syntax. Natural language exhibits sensitivity to word order and grouping, motivating systems like the Lambeck calculus, which rejects commutativity and, usually, associativity. Several well-known logical systems fall under the substructural umbrella. Relevance logics. These typically reject weakening and sometimes contraction, ensuring that premises are genuinely used in deriving conclusions. Linear logic famously rejects both weakening and contraction in its core fragment, modeling reasoning with limited resources. Other contraction-free logics. Various systems study the effects of banning duplication of premises while retaining other structural principles. The Lambeck calculus, a logic originally developed for syntactic analysis of natural language, rejecting weakening, contraction, commutativity, and, usually, associativity. S, T, and T, S. These are substructural systems studied in proof theory and semantics, often related to relevance and display logics, with finely controlled structural behavior. Each of these systems results from a different choice of which structural rules to allow. The syntax of substructural logics is often similar to that of classical propositional logic, with connectives such as conjunction, disjunction, and implication. However, many systems distinguish multiple kinds of conjunction or implication to reflect different structural properties. Proof-theoretic syntax is especially important. Sequence may involve structured collections of premises rather than simple sets, making order and grouping explicit. This allows the logic to encode the absence of commutativity or associativity directly into its formal language. Substructural logics admit a variety of semantic frameworks. Common approaches include relational semantics, often using ternary relations, especially for relevance and linear logics. Algebraic semantics, such as residuated lattices, which model the interaction between conjunction-like and implication-like operations. Resource semantics, where formulas represent consumable or transformable resources. These semantics reflect the restricted structural behavior of the logics and explain why certain classical inferences fail. Basic substructural logics can be extended in many directions. Predicate versions introduce quantifiers while preserving structural restrictions. Modal extensions add notions such as necessity or possibility, often controlling which structural rules apply in modal contexts. Hybrid systems combining substructural logic with temporal, epistemic, or deontic logic have been explored, particularly in computer science and philosophy. Metalogical properties of substructural logics vary widely. Many systems are sound and complete with respect to appropriate semantics. Some are decidable, while others are highly expressive but computationally complex. Cut elimination, interpolation, and normalization results are often central topics of study, though whether such properties hold depends heavily on which structural rules are present. Substructural logic provides a unifying framework for understanding a wide range of non-classical logics. By focusing on the role of structural rules, it reveals how deeply assumptions about relevance, resources, and order are built into classical reasoning. Rather than rejecting logic, substructural approaches aim to refine it, offering logical systems better suited to diverse philosophical, linguistic, and computational purposes.